All right. In this lesson, chapter 5, section 2, we're going to cover logarithmic functions, right? So a logarithmic function is essentially the inverse of an exponential function, right? So if you have something like x squared, the opposite of x squared is like the square root of x, right? If I have 2 times x, the opposite is x divided by 2, right? These are opposites of each other, right? If I have x plus 1, the opposite is x minus, right? These are all opposites of each other, inverses. Even with like sine and cosine, if you remember from geometry, if I have sine of x, the opposite of sine of x is sine inverse of x, right? You can use that button on your calculator to find the sine inverse of a number, right? So if I have an exponent, like let's say 2 to the power of x, we know that this is an exponential function. The opposite of this, and what's going to undo this function, is something that looks like log with a base of 2 of x. All right, and I'll explain a little bit more of this notation in the next slide. All right, so this is how you would switch between a log function and an exponential function. All right, so notice that we have all the same numbers here, right? So we have a base of a right here. We have this y, and then we have this x right here. All right, so all of these show up whether it's an exponential or a logarithmic, right? So it's just a matter of switching between the two. So first I'm going to make a note, right? I know you guys haven't seen this notation before. This log with this a and this x, I would read it as log base a of x, right? So when people are learning this for the first time, I hear all sorts of crazy things, like maybe they say like log a times x or log ax. Those aren't super clear, right? So you need to be a little bit clearer about what each number is doing in this expression, right? A, this little number right here, is your base. X is what's the input of your log function, and then y is going to get you your answer. And notice that y in the log function is the exponent in an exponential function, right? Notice that your bases are still going to be bases, right? A is a base in both of them. Y is going to be your exponent, right? So the answer to a log equation is going to be an exponent. And then notice that your answer as an exponential equation is going to get you the inside of a log equation. So they go hand in hand. I'll show you in the next slide how you can relate the two. Okay, so we're going to convert from log to exponential or vice versa. 1, 2, and 3, we see log in our original problem. So we're going to convert those to an exponential function, right? So I'm going to look at the first one. I have log base 2 of 8 equals 3, right? So again, that is log base 2 of 8 equals 3. That's how you would read this whole thing. All right, so please try and get used to saying it correctly, right? I know it's easy to just say the numbers that you see, right? And a lot of you do the same thing with, like, if I gave you something like x squared, a lot of you will try and tell me x2 or something like that, right? It's x to the power of 2 or x squared or x to the second power, right? So there's a proper way to say these things, right? It's log base 2 of 8 equals 3. To convert this to exponential form, I like to circle the base and then loop all the way around, right? So this little loopy arrow is going to tell you what your answer is. So bases are going to stay a base, so I'm still going to have a base of 2, and I'm going to raise it to the power of 3. That's the next number that you hit, and this is going to equal the number that you end up at after you loop around, and it's going to get you 8. So this would be this equation as an exponential equation. All right, and that's all you have to do. I'm just switching between the two in this page right here. And you can verify that this is true, right? 2 to the power of 3 is equal to 8, right? 2 times 2 times 2 is 8, right? So these are both true statements, right? Log base 2 of 8 equals 3. This is a true statement, and so is 2 to the third equals 8. Another way that you could do it is label in a log equation, your base is going to be this little number right here. Your answer at the very end of it, this is going to end up being the exponent of your exponential function. And this right here is going to get you your answer to an exponential function, right? So you could also remember bay, right? So some people find that helpful. Some people get confused with the arrow. But no matter how you do it, you should get the same thing, right? So if you look at number 2, right, what's your base here? It's 1/2, right? So you read this as log base 1/2 of 16 is -4. Right, so I like to circle the base. I know that I'm going to raise 1/2 to some exponent, right? And that exponent is just going to be whatever you get when you loop around, right? So 1/2 to the power of -4 is going to get you, the number that you end up at is 16, right? And you can verify that this is true, right? If you do 1/2 to the -4, you can make it positive by flipping it, and then you get 2 to the 4 is 16, right? You do get that that's true. Right? Or, again, guys, you could do bay, right? Base, answer, exponent, right? Your base is 1/2, your exponent is -4, and that's going to equal 16. All right? So, same thing with number 3, right? I'll even do it the other way this time, right? So, our base is going to be 10. So, I know it's going to be 10 to some power, right? Our answer is going to be this right here, this 100,000, and then e at the very end, this is going to be your exponent. So, 10 to the power of 5 is going to get you 100,000. All right. Or similarly, you could circle the base, loop around, you end up at this number right here. All right. Same thing with number 4, right? 4, 5, and 6, you see that these are exponential equations, right? And we want to change these to logarithmic, right? They go hand in hand. So you can do the same thing, right? Circle your base. Your base in the exponential equation is going to be the big number that has the little number up top, right? That little number is your exponent. So if 5 is your base here, I would write log with a base of 5. The base in a log is this little number, right? And then loop around, I have log base 5 of 25 is going to equal our exponent here is going to get you 2. So again, base, answer, exponent, right? It's going to equal your exponent in a log equation, right? And then same thing with number 5, right? You can circle your base. Your base is going to be 3, right? So I'm going to have log base 3, and then loop around. We end up at 1/81, and this is going to equal whatever you end up at, right? Is going to be -4. All right. So same thing with number 6. Your base here is this 3/4 right here. So we're going to have a log base 3/4. And I'm going to loop around, right? Of 1 is going to equal the number that you end up at is your exponent up top. It's going to get you 0. All right. And you can always label it if you're ever unsure, right? B, A, E, right? E is your exponent, B is your base, and then A is the answer. All right. So should be pretty simple, right? We're just converting between the two, right? Nothing super crazy. We haven't really solved anything yet. All right, so these are a couple properties of logs. You don't really have to memorize them because a lot of you, what you guys are going to do is you're going to convert a log equation to an exponential one because that's what you're more familiar with. All right, there's nothing wrong with that, but I'm just going to go through these to make, I don't know, if you do these problems enough, you're going to see these properties show up and it's going to make the problems a little bit easier, right? So in this first one, log base A of 1 is going to equal 0. And this makes sense just because if you were to convert it to an exponential, right, we have a base A to the 0, right? A is still your base, and we raise it to the 0 power. This is going to equal 1, right? And anything to the 0 power is going to get you 1. So it makes sense if you think about it with exponents, so it's going to make sense if you treat it in a log equation. Right, so same thing with the next one. Log base A of A is 1, just because, right? Treat it like an exponent. Raise A to the power of 1, and what do you get? Anything to the power of 1 is itself, so A to the 1 is A. Right, and this right here should be in the exponent. Right. log base a of a to the x is going to equal x, right? Not sure what that and is there for. But if you convert it to a log equation, to an exponential equation, right? Your base is a, raise it to the power of x. A to the x is obviously going to get you a to the x, right? So with numbers, right? So a lot of you guys like the numbers examples when I did it in class. If I have log base 2 of 2 to the third power, right? What does this have to equal, right? Well, what do you need to raise 2 by? So in any log equation, you're asking in your base, what do you need to raise the base by to get this as your answer, right? And 2 to the third, all you have to do is raise 2 to the third power, right? So your answer right here is going to be 3. Essentially, what you can also do is keep in mind log and exponents are opposites of each other. So if I have the same base, you can cancel them out and you're left with your exponent. All right. Now in number 4, if I have log base a of x is going to equal log base a of y, then x equals y. This is our one-to-one property of logs, right? And we did the same thing with exponents, right? If I had a to the x equals a to the y, then x equals y. Right? So it's the same thing with logs, right? With logs, if they have the same base, you can cancel out the bases, and then whatever you're left on the inside is going to get you your answer. Right? So similarly, if I had log base 2 of 8 equals log base 2 of x, right? These both have a log base of 2, so I'm going to get 8 equals x, right? Something like that. Okay, so I had just finished recording, but I want to go back and say this and right here. I'm pretty sure there's something that's supposed to be here, and if not, I'll just tell you what it is anyway, right? I didn't go over it in class, so I'll go over it in class next time I see you guys. But what kind of goes hand in hand with this property right here, with this property number 3, is something like this. Okay, I'm sorry, let me erase my example. Right here, let me erase. Whoa, why is it not erasing? Sorry, give me a second. Okay, let me erase this example here. I'm gonna say what's gonna go hand in hand with this property here is if I have a to the log base a of x, right? Similar thing is that your logs can cancel out. So this is gonna equal x as well, right? So just like the other ones, this a and this log base a are going to cancel out. But if you didn't recognize that, you would probably want to prove it, right? Convert it to a log equation, right? If you convert it to a log equation, right, remember, circle your base, loop around, right? If a is your base in an exponential equation, then it's going to be the base of a log equation. So you get log base a of x is going to equal this right here, equals log base a of x, right? So it is true, it's going to be equal to each other, right? Not always are you going to want to convert it to the log form though, right? You're going to want to use or take advantage of the property and just simply cancel out log base a, and then just be left with x, right? So that might be a little bit confusing now, right? But we're going to do an example later on, right? And that's what kind of brought me back here is I was looking through the notes and I saw that there's an example later on where this property shows up, right? So I'd rather talk about it right now, right? All right, so let's try some examples. Now we're actually solving for something. We're solving for x, so it's not as simple as just convert from log to exponential or exponential to log. Let's look at number 7. Right, so I have log base 2 of 32 equals x, right? One way that you could do it is by using the properties of logs, right? So property of logs says that if I have the same base, then you can just cancel them out, and that's what you're left with, right? That's the one that I had just finished explaining, right? So 32, I have 32. I can change 32 to be 2 to the power of 5, right? So then we end up with log base 2 of 2 to the 5th. Well, these are going to cancel out, and you just are left with 5. So you get 5 equals x, right? You can't really see that well, right? So log base 2 of 2 to the 5th is going to equal 5, and this equals x. Okay, you could do it this way, but I did it in class with I think 1 or 2 classes, and it was kind of confusing for some of you. So what you can do is, if you're more familiar with exponential form, you can always convert it, right? Change it to exponential form, right? Make it 2 to the power of x equals 32. And then from here you can convert. You're still going to have to change 32 to have a base of 2, right? So we get 2 to the power of x equals 32 is still going to be 2 to the power of 5. And then this is more familiar to you guys. Using one-to-one property, you can cancel out your base of 2, and then you still get x equals 5. All right, so you guys might like that a little bit more. All right, same thing with the next one, right? I have log base 4 of 2 equals x. So what I'm going to do is you can convert it to exponential form, right? If your base is 4, loop around, you're going to end up with 4 to the power of x is going to equal, we end up at 2, right? So you could probably do this, some of you, without having to do a whole lot of work. You know that what do we need to raise 4 to the power of to get a 2, and it's going to be 1/2. We know x should be 1/2 because 1/2 as the exponent is the same as square rooting, right? But maybe you didn't recognize that and you still want to get the same base, so you can use 101 property, right? 4 we can change to 2 to the power of 2 to the power of x equals 2, and then you get 2 to the 2x equals 2. And then what do we need to raise 2 to the power of to get a 2? And it's going to be 1, right? This is the same as 2 to the first power. So we get 2x equals 1, and then you can still divide both sides by 2, and then you still end up with the same answer of x equals 1/2. Right? So either way, you get the same answer. All right. Same thing with the next one, right? If I have log base 3 of 1 equals x, right, change it to exponential form. 3 to what power is going to get you 1, right? This one should be a fairly simple one, right? Because if you raise any base to the power of 0, you get 1, right? So we really don't need to do a lot of work here. X is going to equal 0, right? And as a matter of fact, this is actually one of our properties. If you look at the previous slide, we talked about our properties. We end up with log base anything of 1 is going to equal 0, right? So you don't have to do a whole lot of work there. All right. Same thing here, right? Log base 10 of 1 over 100 equals x. You can change it to exponential form if you'd like, right? If that'll make it a little bit easier, right? So if I have 10 as my base, change it to exponential, I get 10 to the power of x is going to equal 1 over 100. All right, and we can change it to have a base of, we can change 1 over 100 to have a base of 10, right? 100 you can write to have a base of 10. So you get 10x is 1 over 10 squared. And then you can bring this to the numerator by changing the sign of your denominator. So we get 10 to the x is going to equal 10 to the negative 2. And then all you have to do is cancel out your 10s, and then you get x equals negative 2. All right, same thing with the next one, right? 11. This one you can actually use one of your properties, right? Log base anything of 1 is going to get you 0, so very simply I can just say x equals 0. Don't have to do any work there, right? If that confused you, change it to exponential form, right? 6 to the power of x equals 1, and then think about it. What do you need to raise 6 by to get 1 as your answer, right? And the answer is 0, right? Anything to the 0 power gets you 1. All right. So same thing here, right? You can change this to exponential. So we get 5 to the power of x is going to equal 1 over 125. 125 you can write with a base of 5 as 5 to the third power. And then you can bring 5 to the third power to the top by changing the sign. So we get 5 to the x equals 5 to the negative 3. Cancel out your bases, and then you get x equals negative 3. Right, so hopefully you see, not super difficult at all. All right, let's keep going. Number 13, we can do the same exact way, right? Our base is 7, and 7 to the power of x is going to equal 343, right? You can convert it to exponential. And then 343, this is the same as 7 to the third power, right? So you can go ahead and cancel out your bases, right? So you get x equals 3. I know a lot of these numbers we've worked with a lot before, like 27, 125, like 64 are things that you should recognize. 343, we haven't really seen a lot. What you guys typically do is, I see, especially on your tests and quizzes, right? You guys like to multiply the same number over and over again. And that actually works fine, right? Because we know that if we're going to have to end up using one-to-one property, you guys don't get a calculator for this. You should know that 343 gets you something, or 7 to the power of something, right? So keep trying it and then see what that gets you as your exponent. And then if you try it, you'll do 7 times 7, which is 49, times 7 again. Should get you that 343. All right, so good to double check your work. This one's a little bit different. If you look at this problem compared to the other ones, you see that your base is now the variable, right? But we can do it the same way, right? If my base is the variable, I'm going to have x to the power of 3 is going to equal, we end up at 8 over 27. All right, now this just becomes a cubic equation. So to get rid of a cube, what you got to do is cube root. Right, so you can go ahead and cube root both sides. And then this cube root cancels with the cube, and then you get x equals cube root of 8 over 27. And then remember, if you have a fraction under a radical, you can go ahead and split that up. So you get the cube root of 8 over cube root of 27. And then you get x equals 2 over 3. All right. Try the same thing with the next one, right? This one is different, but for a different reason, right? So this one we have a base of 4, and then bring it around, you get 4 to the power of 5 over 2 is going to equal x, right? And 4 to the power of 5 over 2, remember fractions in the exponent, this was way back. That denominator is going to become the index of your radical, and then so you end up with the square root of 4 to the power of 5, and the square root of 4 is going to get you 2, and 2 to the power of 5, if you multiply it by itself 5 times, is going to get you 32. All right, so x is going to get you 32. All right, let's try the same thing here. All right, so I'm going to go ahead and change this to exponential, right? 49 to the power of x is going to equal the cube root of 7. Right, I see a 49 and I see a cube root of 7. I would think that you can change both of these to have a base of 7. So 49 is the same as 7 squared. You get 7 squared to the x is going to equal 7 to the 1/3. Right, remember that cube root is the same as to the power of 1/3. And then we get 7 to the 2x is going to equal 7 to the 1/3. So then you can go ahead and cancel out your bases, and then you get 2x equals 1/3. Right, you could divide by 2. A lot of you, though, if you see 1/3 over 2, are not going to know what to do. Right, you might get stuck there. Right, so I would instead multiply both sides by a half. And then if you do that, 1/2 and 2 cancel out, and you get x equals 1/6. All right, something like that. All right, let's keep going. All right, so this one right here, we can do 5 base of 5 to the power of x equals 1 over 625. I see a base of 5 here. I see a 625. We would think that that could get you something with a base of 5, and it can, right? So we get 5 to the x is going to equal 1 over 625 is the same as 5 to the power of 4, and then you can bring that to the numerator by changing the sign of your exponent. So we get 5 to the x equals 5 to the negative 4. Cancel both sides, and you get x equals negative 4. All right, and keep going. We have log base 10 of 0.001 equals x. All right, a little bit different because it's a decimal, but same idea. We get 10 to the power of x is going to equal 0.001. If the decimal is confusing to you, change it to a fraction, right? We've worked with fractions a lot before. I know you guys aren't big fans of them, but we haven't really done a lot of decimal practice, right? So what you can do is you can convert the decimal to a fraction, right? So remember, we have a decimal point right here. We can go 1, 2, 3 units over. and that gets us the 1. And since we move 3 units over, we're going to have over 1,000, right? 3 zeros. So then we get 10 to the power of x is going to equal 1 over 1,000, like that. And then this looks like something that we can solve, right? 1,000 is the same as 10 to the power of 3, right? With the powers of 10 are easy, right? You just look at the number of zeros that it has. And then 10 to the power of 3 you can bring to the top. And then we get 10 to the power of x equals 10 to the negative 3. And then you can go ahead and cancel these out, and so you get x equals negative 3. All right, and that's it for this page. All right, let's keep going. Number 19, we can do the same thing. It's not written in the same way that we usually make it, so we can still make this equal x on this side, and then do the same little loop around that we normally do. Another thing that we can do, like I had mentioned before, is you can change this cube root of 4. What did I say? 4th root of 8 to be 8 to the 1/4. And then you can use a property of logs to cancel out your bases, right? So if I have a log base 8 of 8 to the 1/4, this is going to equal 1/4, right? So we get x is 1/4, right? Or as before, you can change this to exponential form, and you get 8 to the x equals 4th root of 8. But you would still, regardless, have to change that 4th root of 8 to 8 to the 1/4 to be able to get your answer, right? So either way, you end up with the same thing, right? So if you recognize the property of logs, then it should have been a little bit quicker, all right? And then this one, number 20, this is what I added on to that one slide with the properties. If you have the same base in both the log and the exponent, it doesn't matter what order they show up in, right? As long as it's a base, they have the same base, then they're going to cancel out. All right, so this one, for example, 3 and log base 3 are going to cancel out, and you get x equals 8. Right? If you aren't comfortable with that, right, write it as a, right, so let me just rewrite it. Convert it to an exponential equation, right? I have 3 to the power of x is going to equal, change it to a log equation. It's going to be log base 3 of x is going to equal log base 3 of 8. And then we can use one-to-one property of logs and say that log base 3 can cancel out of both of these. No matter what, you're going to get x equals 8, right? But you're not going to want to do it the long way every single time. If you know the property, you can just go ahead and use it, all right? So same thing with number 21, right? You could convert it, right? Say 2 to the power of, not 2 to the power of x. Log base 2 of x is going to equal log base 2 of 9, and then cancel out your logs, and then you get x is 9, right? That didn't take that much work, but you could also very simply cancel out 2 and log base 2 and very simply get 9 equals x, right? Either way, you get the same answer, right? So this is where your properties are very useful. All right, so let's do the same thing over here. I'm going to go ahead and convert this to exponential. So we get x to the negative 2 is going to equal 25. All right, so let's see, what can we do to this 25 to change it to a negative 2? Well, I know how to get it to a positive 2, and that's by changing 25 to be 5 to the power of 2. And then this is going to equal x to the negative 2. Right, so to make that to a negative 2, we're going to flip it and move 5 to the bottom, right? But if you do 1 over 5 to the negative 2, right, that's not quite apparent what happens, right? But keep in mind, right, so I'm not going to write it that way. What you could do instead is you could say x to the negative 2 is 1/5 to the negative 2, right? This is still the exact same thing, right? And even if you did it the other way that I had scribbled out, 1 to the negative 2 is just going to get you 1, right? 1 to any power is going to get you 1. So writing it in this way, we can see that we can cancel out now our exponents, and then we get x equals 1/5, right? So for a problem like this, where maybe you're not so certain, right? So maybe that still confused you a bit as to how we got our answer, right? Plug it back in, right, and see if it makes sense with the original problem. All right. 23 should be a fairly simple one, right? If you go ahead and take this 4 and write it to the power of 3, this equals x, right? 4 to the power of 3 is just going to get you 64. All right, so 64 equals x. All right, and then this one right here, right, same thing. We can go ahead and change it to exponential, right? This is written in the reverse direction. So I would say 4 to the power of x is going to equal cube root of 16. Right, and then 16, I know that I can write that as something to the power, or something with a base of 4. So you get the cube root of 4 squared is going to get you 4 to the power of x. And then 3 in the index of our radical is going to become the denominator. So you get 4 to the x is going to equal to the 4 to the 2/3. Right, and then again, like before, you can cancel out your bases, and you get x is 2/3. All right, so now the last part of this lesson, we're going to talk about something called a natural logarithm. Right, so in the previous lesson, I had talked about the natural base e. I didn't call it the natural base, I just called it e, right? But we call it the natural base, right? So the natural log is a log that has the natural constant as its base, right? So if you see ln, right, and if you use a scientific calculator, you see that button ln. That ln is the same as log base e, right? Another thing to note is that the regular log button in your calculator, you don't see a number in the subscript, right? So if you don't see that number, you assume it's 10. So log base 10 of x is the same as log of x, right? If you don't see a base, assume it's 10. And same thing with ln. If you see an ln, assume the base is e, right? So they're gonna have the same properties as though it was just a regular log with a base, right? So again, this is the same as log base e of 1, right? And of course, log of 1 is always going to get you 0, right? Because anything to the 0 power is 1, right? Same thing over here. This is the same as log base e of e equals 1, right? I can go ahead and change this to exponential, and then you get e to the first is e, right? Same thing as we had established before. Same thing here. If I have log base e of e to the x, right, the log base e and the e can cancel, and you're just left with x, right? And then ln of x and ln of y, you can just cancel out ln, right? And then just like before, this one right here, you can change this to be e to the ln of x is x, right? Because just like before, e to the log base e of x, you can write this in exponential form, right? If this equals x, if you write it in, I'm sorry, not exponential, in logarithmic form, you get log base e of x equals log base e of x, and that is true, right? So we're going to use these properties in the remainder of this lesson. I didn't mention it, but I skipped the graphs for this lesson, right? Whether we go back to it in our course or not is to be determined. But just for this lesson, I'm skipping the graphs. If we get back to it, again, we're going to do it another day in another video, or I'll just leave it out entirely, right? You'll know in due time. All right, you guys, 7 more examples in this lesson, and they're all have to do with ln. All right, so let's start with 29. 29, I have ln of 1 over e equals x, right? Couple things that you could do here. Change ln as log base e of 1 over e equals x, right? And that way, this way, you could change it to exponential form. And then I would go ahead and have e to the x equals 1 over e, and then you can see that to bring e to the top, you just have to change the sign of the exponent. So you get e to the x equals e to the negative 1, cancel out your e's, and x equals negative 1, just like we did before, right? The only thing that was new was you had to change ln to log base e, right? Number 30, right, same thing, except you have a property, right, e to the ln is always going to cancel out. So we get x equals 5, right? That's always going to be true if you have the same base, right? So if you didn't recognize that, you can change it to log base e of 5, and then hopefully here you can see that you have the same base. Or even if you didn't, change it to a logarithmic equation. Then you get log base e of x equals log base e of 5, right? And then you can cancel out your log base e's, and then no matter what, you still get x equals 5, right? So lots of different ways to do it, but they're all pretty straightforward and simple, all right? So let's look at this one, right? Same thing here. ln e is going to cancel out. That's a property. That's going to get you 1, right? And if you're not okay with that, what you can do is say, okay, here, log base e of e, write it that way, and then you can see that log base e of e, because they're the same, it's going to get you 1. So you get x equals 2 times 1, so x equals 2. All right. So same thing over here, right? ln and e are inverses of each other, so they're going to cancel out. So we get 1/3 equals x. Right? And all of these, you really don't need that much work. You just need to get familiar with the properties. If you're not familiar with the properties, what you would do is you would change it to exponential, right? So change it to log base e of e to the 1/3. And then hopefully here the property is more apparent because you can just cancel out. But if it's not, change it to exponential. We get e to the x equals e to the 1/3. And then now here you can cancel out your e's, right? So no matter what, you get x equals 1/3. All right. Let's try the same thing over here, ln of 1. This one should be super quick also, right? Because ln of 1 is the same as log base e of 1. And log base anything of 1 is going to get you 0. So you get 5 times 0 is x, right? So x equals 0. All right. Keep going. And this one right here, I have 3/4 ln of e is x, right? Again, ln of e, that's the same as log base e of e. So this right here is going to get you 1, right? The logs cancel out. And then you get 3/4 times 1 is going to get you x, right? So very simply, x is 3/4. All right. And then last one right here, same thing here. E and ln are going to cancel out, so you get 7 equals x. If you didn't recognize that, change it to e log base e of 7 equals x, and then circle your base, loop around. You get log base e of x equals log base e of 7. Use your 1-to-1 property, cancel out your log base e's, and no matter what, you get x equals 7, right? So this slide actually went pretty quickly, right? We didn't spend that much time on these problems. I just showed you a couple of different ways to do some of them. But using properties, it makes them super easy, right? So this lesson hopefully wasn't super difficult. This entire video covers A and B. If we do part C, which is graphing, then that'll be in another video. But for this video, I'm leaving graphing out, right? But this covers both parts A and B, right? So the 2 days that we're doing this lesson.